Astronomers noticed a number of small objects, a mysterious planet lurking out in the edges of our solar system. This Neptune-sized world orbits way out past Pluto.
Astronomers have spent years chasing a hidden giant beyond Neptune, an invisible heavyweight that only reveals itself through the strange dances of icy worlds at the solar system's edge. They call it Planet 9, and no telescope has ever caught it. Then, in their hunt for clues, researchers uncovered a jaw-dropping twist, a cosmic surprise that changes everything we thought we knew. Stay with us to discover how this unexpected find rewrote our space story. The sneaky blip. While the world's eyes were fixed on the James Webb Space Telescope chasing the faint glow of galaxies billions of light-years away, a small team of researchers from the US and Canada, led by Sihao Cheng, was busy sifting through years of dusty telescope snapshots.
There might be a ninth one. I have some opportunity in the search of Planet 9. Maybe I can find it in near future.
They weren't looking for distant beacons, though. They were hunting for something much closer to home, Planet 9. They dove into 7 years' worth of images taken by the Dark Energy Camera in Chile and the Canada-France-Hawaii telescope. Night after night, they scanned for tiny smudges of light, the kind that, at first glance, might be dismissed as noise or a stray pixel. But patience paid off. 19 separate sightings of the same faint speck emerged, spaced out over those 7 years. That was enough to trace its path around the sun. They called their find 2017 of 201, a name that might sound like someone's Wi-Fi password, but it marked a milestone. 2017 of 201 is a dwarf planet candidate, and may be the brightest known object in the solar system that is yet to have a directly measured size. By plotting those 19 blips, the team pieced together its orbit. It wasn't a smooth circle like Earth's or Neptune's. It was stretched and tilted, swinging the newcomer far above and below the plane of the planets we know so well.
Occupied all of these eccentric orbits that went every which way. This field of debris, which was initially completely random.
Astronomers have noticed something strange beyond Neptune. Several distant space objects, trans-Neptunian objects, or TNOS,
as with the rest of our survey, I found a really bright object,
aren't moving randomly as you'd expect. Instead, many of their orbits are tilted, stretched, and pointing in the same direction, suggesting a massive unseen Planet 9 is tugging on them from the dark. But this newcomer doesn't fit the pattern. Its orbit is completely off. If Planet 9 is real and pulling the strings, 2017 of 201 shouldn't hold such a stable yet odd path. But what exactly is this odd little world made of? And could it be just one of many hiding in the dark?
But wouldn't it be cool if Planet 9 affected also something else, something outside of the Kuiper Belt? Turns out it does.
The Scarlet Wanderer. 2017 of 201 stands out in two big ways: its deep red color and its hefty size. When astronomers measured how it reflects light, they found a color index of about 0.77 plus or minus 0.11 magnitudes. That puts it close to Sedna's ruby hue, and far redder than our sun. In the world of distant icy bodies, red usually means old, processed surfaces, stone and ice that have been baked by cosmic rays for billions of years. The team didn't see any flicker or wobble in its brightness beyond 0.1 magnitude. In plain terms, 2017 of 201 doesn't spin wildly or carry a big moon casting shadows. It likely keeps a round shape, more like a smooth ball than a lumpy rock.
Planet 9's gravity is really a shepherding effect to the stable, distant Kuiper Belt objects that we see.
To catch any subtle changes, say a fast rotation or a tiny satellite passing in front, we'll need deeper, faster snapshots from powerful telescopes. Next came the big question: how big is this thing? Astronomers start with how bright it looks from Earth and how far away it is. Then they guess how shiny its surface might be, that is, its albedo. Using Find Orb software on their photometry, they pegged its absolute V-band magnitude at HV equals 3.5. An albedo of around 0.15 fits the trend seen in similar distant objects, so they plugged that in. The result, a diameter near 700 kilometers. At that size, gravity would have pulled 2017 of 201 into a nearly perfect sphere, earning it the same dwarf planet status as Pluto.
that had ever been found in the outer part of the solar system since Pluto. And this was pretty exciting.
Even more exciting is what this object says about its hidden companions. 2017 of 201 is bright enough to show up in surveys for less than 0.5% of its 24,000-year orbit, right around perihelion. That tiny window means thousands of siblings, just as big and just as red, could be hiding in the cold darkness, too faint to see most of the time. Finally, the team crunched the numbers en masse. Assuming a density of 1.7 grams per cubic centimeter, that 700-kilometer sphere weighs in at about 3 times 10 to the power of 20 kilograms, roughly 1 in 20,000 of Earth's mass. If 2017 of 201 is just one of 1,000 similar worlds, their combined mass could reach about 1% of Earth's mass. That's roughly the weight of our moon. Compare that to the known Kuiper belt, 1 to 2% of Earth's mass, and the scattering disk, at 1 to 2%. These extreme objects pack a serious punch. In short, this scarlet wanderer is more than a lonely traveler. It's the tip of a massive iceberg. Each discovery of a red round dwarf planet on a wild orbit tells us just how much more the outer solar system has in store. With future thermal measurements from ALMA, astronomers will lock down both size and albedo for 2017 of 201. And the hidden population it represents will step further into the light.
Gravitational one-way sign is confining these orbits, keeping them clustered and pulling them all into the same plane.
Edge Wanderer. Instead of a neat circle, 2017 of 201's orbit stretches from about 44.9 astronomical units at its closest to 1,610 astronomical units at its farthest, making it an extreme outlier in our solar system. This object completes one full circuit around the Sun in roughly 24,000 years. Its path is extremely elongated, with an eccentricity of 0.95. That means more than 99% of its journey keeps it deep in darkness, too faint to see from Earth. It only shows up for a short time when it comes closest to the Sun, a point called perihelion. The last time that happened was in mid-November 1930. As of July 2025, it sits about 90.5 astronomical units away, ranking among the solar system's farthest known travelers. Eritus Yang, one of the co-discoverers, points out that finding 2017 of 201 suggests thousands more lookalikes lurk too far and faint to spot, hidden in plain sight.
It's going to revolutionize the way we think about our solar system, just because we're going to know so much more about what's out there.
2017 of 201's orbit falls in a zone astronomers once thought empty. That region sits near the edge of the scattered disk in the inner Oort cloud. Its perihelion at 44.9 astronomical units keeps it clear of Neptune's direct influence. But over billions of years, that giant planet likely gave it a strong push outward. After escaping Neptune's dominant pull, the gentle tug of the Milky Way, known as the galactic tide, lifted its closest point even higher. Close encounters with passing stars could have nudged it further still. Yang and the team believe more than one gravitational shove shaped its journey. A large planet, possibly Neptune in its youth, or an even more distant world, may have first cast 2017 of 201 into a distant orbit. From there, interactions within the Oort cloud could have flung it back inward to its current track. This finding challenges our view of the solar system's outer reaches. Each extreme trans-Neptunian object offers clues about how planets form and migrate. They reveal a past filled with chaotic movements, planets shifting, stars passing close by, and the galaxy's tidal forces at work. Yet shaping such a wild, lopsided orbit through the quiet outskirts of the solar system would take more than just a single push. Gravity's hidden hand. 2017 of 201 didn't start its life on the smooth path we see today. Its journey began close to Neptune, where the giant planet's gravity gave it a strong shove. That initial kick sent it outward on a stretched orbit, but Neptune alone couldn't push it all the way to 840 astronomical units. The math shows that changing its path so much would take longer than the age of the solar system if only Neptune were at play. Once 2017 of 201 reached the far reaches, something else took over. The Milky Way's gentle tug, known as the galactic tide, and rare visits from passing stars. These forces acted like slow, invisible hands, lifting their closest approach away from Neptune. Over millions of years, the object's orbit detached, rising into a region where planetary pushes are weak. In this quiet zone, its path settled into the steady track we see now. To test this story, researchers ran a series of backward simulations, rewinding 3.5 billion years of the object's life. They didn't just try one version. Instead, they created 100 different histories, each starting with slightly different orbital details based on what we observe today. Watching how each version evolved, they saw a clear pattern. First a big kick by Neptune, then a slow lift by the galactic tide, and finally, a gentle pull back inward when perihelion dipped too low.
There isn't another kind of natural mechanism to generate these highly inclined bodies.
In these simulations, the key player is angular momentum. Think of it as the object's orbital spin. The galactic tide slowly drains that spin, making the perihelion drop. Once the orbit swung back into reach of Neptune's weak pull, the dwarf world got nudged inward, tightening its path. This two-step dance, first outward, then inward, matches the orbit we observe today. This scenario doesn't prove exactly how 2017 of 201 got to its current track, but it shows the path is possible. It paints a picture of a rough ride, a wild scattering by Neptune, a patient lift by galactic forces, and a final tweak back home. Each step took millions or even billions of years, but together they explain how an icy rock can travel from the crowded Kuiper belt all the way to the edge of the solar system and back. Understanding this journey helps scientists unlock the history of the outer solar system. If 2017 of 201 took this route, many other distant objects likely did too. Each new find offers another clue about the hidden forces shaping our cosmic neighborhood. Gravity's hidden hand may be gentle or fierce, but it leaves a clear trail in the long, winding orbits of these distant wanderers. A brief spotlight. 2017 of 201 spends just 1% of its 24,000-year journey close enough to catch our telescopes. That tiny window means we might have spotted it at exactly the right time. If so, this glimpse could be the tip of an iceberg, hinting at dozens or even hundreds more icy worlds with similar long, lonely orbits waiting in the darkness. Right now, this dwarf planet sits closer to the Sun from Earth's point of view.
All of their orbits kind of point into the same direction.
Telescopes on the ground can pick it up, but only for a little while longer. Researchers need to wait about a month before the geometry lines up again for detailed follow-up. In the meantime, they're hopeful the James Webb Space Telescope can scan it too. Webb's powerful infrared eyes could reveal surface features, measure its temperature, and even spot a tiny moon if one is hiding there. While astronomers prepare for those observations, the question of Planet 9 still lingers. Early simulations used one guess for where Planet 9 might hide, but not everyone agrees on that spot.
Small circle here, small pink circle that is the orbit of Neptune, as well as the orbit of Planet 9.
Konstantin Bedagin, who proposed Planet 9 in 2016, says 2017 of 201 doesn't directly support or deny the theory. As he told NBC News, this object is on a chaotic orbit, and so when it comes to the question of, what does it really mean for Planet 9? The answer is not very much, because it's chaotic.
Gravitational effect, which is keeping all of those orbits confined. As our modeling shows, the only reasonable explanation for that.
Still, Sihao Cheng, the astrophysicist who led the discovery, hasn't given up hope. This whole project started as a search for Planet 9, he says. He sees 2017 of 201 as a win for scientific discovery, even if it's not the giant planet they first sought. Every new extreme trans-Neptunian object adds a piece to the puzzle, revealing how chaotic and surprising our solar system's outskirts can be. So if you're holding out for a ninth planet, don't lose heart. The hunt continues with better telescopes, smarter surveys, and more keen eyes on the sky. And if Planet 9 is out there, moving ever so slowly across the dark, we may yet catch that rare glimpse, just as we did with 2017 of 201.
The dwarf planet is one of the most distant visible objects in the solar system.
Echoing paths. 2017 of 201 isn't alone in its wild journey. Its orbit now mirrors that of another oddball, 2013 SY99. These two icy voyagers share a secret pattern among the solar system's drifters. SY99 was spotted with the Canada-France-Hawaii telescope as part of the Outer Solar System Origins survey. It moves so slowly that mapping its path took patience.
Inner part of the solar system is full of asteroids and comets and all sorts kinds of things, planets, all this stuff.
This small world traces a huge loop that takes about 20,000 years to complete. At its nearest, SY99 comes into 50 astronomical units, that is, 50 times the Earth-Sun distance. Then it swings back out along a stretched ellipse that stretches 730 astronomical units from end to end. Even compared to Sedna or 2013 VP113, SY99 dares to roam farther.
Planet 9's gravity is really a shepherding effect to the stable, distant Kuiper belt objects that we see.
When astronomers trained other telescopes on it, they saw a reddish glow. Measuring its brightness and distance, they estimated it's only about 250 kilometers across, roughly the size of Wales in the UK. SY99 belongs to a tiny club, just 7 known extreme trans-Neptunian objects. These are icy bodies whose paths lie beyond Neptune's reach, but not quite far enough to feel the Milky Way's pull. Their closest approaches sit well past Neptune's 30 astronomical units orbit, so they're detached from the giant planet's strong gravity. Yet when they're at the far ends of their loops, they still hug the solar system too tightly to drift under galactic tides alone.
Explored so much of the solar system beyond those 8 that if there were anything else like a planet, we would have found it.
The matching orbits of 2017 of 201 and 2013 SY99 hint at a shared story. Something must have nudged them onto these vast, lonely paths. Was it a passing star, the gentle tug of the galaxy, or a hidden giant planet out there? Each new extreme TNO we find adds a chapter to this cosmic mystery.
This cosmic tango has been the bedrock of our understanding of planetary mechanics.
As we map more looping paths, these distant drifters will guide us toward the unseen forces shaping the outer frontier of our solar system. But what if this mystery isn't new at all? What if the clues we need have been hiding in plain sight, just like they were centuries ago? Wobbles and shadows. Back in 1781, William Herschel aimed his homemade telescope at the sky, looking for comets. Instead, he spotted a new point of light moving slowly against the stars. It wasn't a comet's tail or a shooting star. It traced a steady path around the sun. Herschel had found Uranus. Over the next decades, astronomers watched Uranus carefully.
This icy ringed world is Uranus. In 1986, NASA's Voyager 2 made the first and so far only visit to the planet.
Its orbit kept shifting ever so slightly. Newton's laws had predicted a smooth path. Instead, Uranus wobbled. Why? Urbain Le Verrier, a French mathematician, ran the numbers by hand and proposed a solution. Another planet must be tugging on Uranus. He even calculated where it should sit in the sky. When observers pointed their telescopes at that precise spot, they found Neptune, exactly where Le Verrier predicted. Fast forward to 2016. Mike Brown and Konstantin Batygin at Caltech noticed odd behavior among distant worlds beyond Neptune in the Kuiper Belt. The Kuiper Belt is a ring of icy bodies out past Pluto. There are thousands of these objects, leftovers from the solar system's birth. Brown and Batygin saw that several of these distant orbits pointed the same way and leaned at similar angles.
The model kept predicting these orbits that are perpendicular to the plane of the solar system, and moreover that these orbits should be visible.
Random orbits should scatter in all directions. Instead, this handful was tightly grouped, as if something big was pulling on them. Their math showed that only a planet 5 to 10 times Earth's mass could herd these Kuiper Belt objects so neatly. This unseen world would circle the sun far beyond Pluto, out where sunlight is a dim glow. They called it Planet 9. No telescope had ever caught it directly. Instead, it was being tracked by its gravitational footprints. Searching for an invisible planet is tough. Light from a body that far out barely reaches us. To chase Planet 9, scientists dug into 2 all-sky surveys in infrared light. The first came from the IRAS satellite in 1983. The second was from Japan's Akari mission between 2006 and 2011. Infrared sees warmth. A cold planet still gives off a tiny heat signature, even if it hides in darkness. A team at National Tsinghua University in Taiwan had a neat trick. They looked for objects that appeared in both surveys, but shifted position. If something moved between 1983 and 2011, it might orbit the sun, just at a glacial pace. Planet 9, if it's there, would creep about 3 arc-minutes per year. That's so small that the full moon, at 1,800 arc-minutes, would dwarf its motion.
It was a gravitational one-way sign towards a distant, eccentric planet in the solar system.
How do you spot such a tiny shift? Parallax comes in handy. Hold up your finger and close one eye, then switch eyes. Your finger seems to jump against the background. That jump is parallax. For distant objects, Earth's orbit around the sun provides 2 vantage points 6 months apart. By comparing where something sits against distant stars at those 2 times, astronomers can measure its shift. If an object moves just a bit, that tells them it's nearby, at least nearby in cosmic terms. By combining these infrared moves with parallax checks, researchers hope to sift true solar system wanderers from distant galaxies and faint stars. Every shifted dot in the sky could be a clue to Planet 9's hiding place. And every clue brings us closer to completing the map of our solar neighborhood, just as Herschel and Le Verrier did centuries ago. Now it's time for today's subscriber pick. They'd been scanning the distant ice giants for decades, convinced a hidden world lurked beyond Neptune. Then, in one dusty telescope frame, something else appeared, a glowing orb weaving through the stars like a dancer. When the team realized that astronomers were looking for Planet 9 when this guy showed up in the telescope image, their jaws dropped. This newcomer wasn't a lonely rock. It pulsed with strange, shifting lights. Some whispered it might be a wandering seed ship from a world where creatures swam in methane seas. Others imagined miniature forests glowing under alien suns, sending out scout probes to explore. In this tale, our solar system isn't just 8 planets and frozen debris. It's the backyard of hidden civilizations. Could there be rogue planets seeded with life, drifting between stars? The race for 9. We might be just a few years away from finding Planet 9, or proving it isn't there. If it exists, this world would be a dark giant, 5 to 10 times Earth's mass, sliding on a long, stretched orbit far from our Sun. Spotting it has been a huge challenge. That's where the Vera C. Rubin Observatory comes in. When it starts full surveys in late 2025, its giant camera will capture more of the sky, deeper and faster than ever before.
All of this is made possible thanks to the observatory's camera, which is the largest digital camera ever built.
Astronomers expect Rubin's steady scans to pick up faint, slow-moving objects, exactly the kind that Planet 9 would be. If the planet is out there, Rubin could find it within a few years. Once we see Planet 9, the next step is to send a probe. But missions take time. Andreas Hein, a space systems engineer at the University of Luxembourg, says planning, funding, and government approvals mean a mission would need at least a decade after discovery. Space agencies run careful reviews to choose which projects to back. Every detail, cost, science goals, technical risk, gets weighed before a mission gets the green light. There's one way to speed things up, if Planet 9 turns out truly odd. Manasvi Lingam, a theoretical astrobiologist at the Florida Institute of Technology, points out that an unexpectedly strange world, a planet with odd chemistry or surprising moons, could spark urgent interest. If initial data show something unique, agencies might push a mission through faster to study the planet's mysteries before they fade from view.
Or, I guess, the idea behind a hypothetical 9th planet somewhere on the outskirts of the solar system.
Private companies could also shake things up. Andreas Hein notes that businesses like SpaceX aren't bound by the same slow government processes. If SpaceX or another commercial launcher wanted to send a probe, they could potentially design, build, and launch a mission within 5 years of discovery. Lower bureaucracy, flexible budgets, and rapid decision-making could make a private expedition happen sooner than a traditional NASA project. Either way, the clock is ticking. Rubin's surveys will start in 2025, and every clear night will add fresh data. Astronomers will sift through millions of images, hunting for that tiny, slow shift in starlight that marks a new planet. If Planet 9 stays hidden, we might finally rule it out. If it appears, we'll face a race to plan, build, and launch a mission while the excitement and funding are high. Mission to the unknown. Recently, a small team of researchers asked a simple question. Once we build a spacecraft for Planet 9, how long will it take to get there? Andreas Hein, Manasvi Lingam, and amateur astronomer Adam Hibbard ran the numbers in a preprint paper on Archwire.
And that shows us that that planet, which we now call Planet 9, must also be.
They based their work on a craft similar to NASA's Voyager probes and assumed Planet 9 orbits about 400 astronomical units from the Sun, 400 times Earth's distance. Their conclusion? Somewhere between 45 and 75 years of travel. At first glance, that sounds like a lifetime.
Planet 9 either doesn't exist or seems to orbit in an entirely different location.
But compared to Voyager 1, it isn't so far off. Voyager 1 launched in 1977, and after 46 years, sits only about 163 astronomical units from Earth. To reach 400 astronomical units in 45 years, a Planet 9 probe would need to travel roughly 3 times faster than Voyager 1. Later studies nudged Planet 9's likely orbit farther out, closer to 500 astronomical units on average, and possibly near 550 astronomical units right now.
If Sedna had had an orbit like this, that kisses the orbit of Neptune once around the Sun, that would have actually been really easy to explain.
That extra distance pushes the trip even longer. But Lingam points out the paper's estimates were conservative. In other words, the 75-year high end still holds up. How do probes pick up speed? They use gravity assists, or slingshots, around planets. Voyager 1 flew past Jupiter, Saturn, Uranus, and Neptune, stealing a bit of each world's orbital energy. That lets it journey deeper into space with less fuel. But each close pass also required the craft to slow down or change direction to line up for the next swing. A Planet 9 mission could skip some of that complexity. Instead of hopping from world to world, it would aim as directly as possible at its target. A straight shot means fewer course changes and more time under the Sun's and planets' gravity wells, boosting its speed outward.
That would have just been an object that had been in a circular orbit around the Sun in that region of icy bodies.
That approach could shave years off the trip without new propulsion tech. Mike Brown, who first co-proposed Planet 9 in 2016, once suggested a clever gravity assist path might cut travel time to as little as 20 years. But even he admits that using today's rockets and mission planning, making a 20-year journey is difficult. That brings us to advanced ideas like light sails. These are giant mirror-like sheets that catch sunlight or ground-based lasers to push spacecraft. In their 2022 paper, Hein and Lingam calculated that a light sail might reach Planet 9 in as little as 7 years. Sounds amazing, until you remember we don't yet have sails that big or powerful. The team figures it could be another 20 years before such sails are practical and cost-effective. Given those timelines, Lingam argues it makes sense to send a conventional probe first. If we find Planet 9 tomorrow, launching a tried and tested design could get us there on a mid-century timescale. Then, if and when laser sails become ready, we could send faster craft later to gather detailed data or deliver instruments. What about people? Visiting a world 500 astronomical units away is a dream for now. Even at light sail speeds, a crewed ship would need decades of reliable life support. However, Hein remains optimistic. He says that in the distant future, perhaps as we develop interstellar travel, humans could swing by Planet 9 on the way to other stars. For now, robotic explorers lead the charge. The decades-long journey to Planet 9 isn't a showstopper, it's a plot point in the biggest story of modern astronomy. As Rubin Observatory and other surveys close in on Planet 9's hiding place, mission planners will be sketching rocket paths and gravity assists. They'll balance speed, cost, and the long wait ahead. A 45-year voyage may span generations, but the first probe to Planet 9 will carry our curiosity further than any spacecraft before. And when that craft finally arrives, it will open a new chapter on the edge of our solar system, one written on the vast highway to the 9th planet.